All right, welcome back everybody. So we're going to look at our second kind of re-representation of the rectangular coordinate system, and this is going to be using polar coordinates. So if you note, we've started with rectangular coordinates as our main focus in the AB course, and now we're going to be moving to, again, two different types of representations. One is going to be parametrics, of course, which we've already discussed. And then now it's going to also be using polar coordinates, so r comma theta. So note that for parametrics, the key idea is the parameter, right? So t is the separate parameter that defines x and y separately, but together they combine to develop our curves. For polar coordinates, we're going to be defined by r and theta, which you could think of as direction and length or magnitude. So again, still this idea of vectors is kind of floating in the background. But for r and theta, instead of measuring our functions as the distance horizontally and then vertically as being our representation of how to get from the origin to a point, we're now going to instead measure an angle and a distance to get to that point. Right? So we'll have theta and r describing the way to get to that point. So again, this is just going to be a slightly different representation of still finding the same coordinates through a different method. But what we need then is we need a way to connect x and y and r and theta. And this we're going to use, again, our kind of basic interpretation of x and y in terms of sines and cosines. So we've got this picture here. So note that y could be written as r cosine theta, x could be written as r sine theta, just by using right triangles and thinking about this as a coordinate on, say, a circle. So we've got x is equal to r cosine theta, y is equal to r sine theta. R then is going to be equal to that familiar sum of the squares. So rad x squared plus y squared. And then theta, of course, is just going to be the arctan of y over x. So these are going to be kind of the common values that we use here. One thing we'll note is that we can augment r to r squared to get rid of the square root, just to get that direct Pythagorean relationship. So r squared is just equal to x squared plus y squared. All right, so for the pole and the polar axis, we also reorient our axes to represent the corresponding measurements, which are no longer the x and y axis, right? So our x-axis is what we call the polar axis. So note this is representing the x-axis, which is 0 degrees, right? So it's representing 0 degrees measured from standard position. Then we have the line theta equals pi over 2, which is representing the y-axis, and of course is just 90 degrees. And then we also have the center point. So note the center is simply called the pole. So the origin is now called the pole. So what that means then is, this gives us a representation of how to draw coordinates in. So we'll kind of get rid of that for a moment. So if we're measuring points, let's pick a few. Let's say 2 comma pi over 6. We could do -2 pi over 6. We could do 4 negative pi over 3. We could do 4 7 pi over 6, And we could do, let's say 3 and then 21 pi over 6. All right, so let's go ahead and graph these. So there's two ways you can do it. You can kind of go direction first and then rotate. Or you can find the line that corresponds to your angle measure first and then measure the distance out. So let's actually write in our angle measures here. So we'll note that we're dividing 90 into 6 pieces, which means each one of these tick marks is really 15 degrees. So this is going to be pi over 6, this will be pi over 4, and this will be pi over 3. We could do, 15 degrees if we wanted to, but typically we're just going to go between 30, 45, and 60. So then on the opposite side, we'll have 2 pi over 3, 3 pi over 4. Oh, whoops. Let's try that again. 2 pi over 3, 3 pi over 4, 5 pi over 6. Some polar graphs won't be as done in these increments. They'll just have these three kind of most commonly used angles. Down here, we will have 7 pi over 6, 5 pi over 4, and 4 pi over 3. Of course, we're going to have 3 pi over 2 pi, and then we'll have 5 pi over 3, 7 pi over 4, and 11 pi over 6. So again, just using those angle measures, we can graph each one of these. So let's do that in red. So along the pi over 6, we're at 2, which means we're going to be representing this point in space. So maybe we'll call these A, B, C, D, and E. So there's A. And then for B, we've got negative 2 pi over 6. So negative 2 is going to be, instead of measuring in the positive direction to the right, we'll measure in the negative direction to the left. So one way we could do this is to go negative 2 units and then rotate pi over 6. Now pi over 6 is positive, so we still measure counterclockwise. So we would end up at what is 7 pi over 6. So negative 2 pi over 6 is the same as 2 comma 7 pi over 6. So our point again is going to be here. However, another way we could have done it is we could have rotated pi over 6 and then measured in the reverse direction. All right, so let's go ahead and try C, which is 4 negative pi over 3. So negative pi over 3 is going to be the same as 5 pi over 3. So we'll measure pi over 3 in reverse, and then we'll go out 4 units, 1, 2, 3, and 4. And that will give us C. For D, we've got 4, 7 pi over 6. So that's going to be right next to B. Just going to be 4 units out instead of 2 units. And then E is 21 pi over 6. So we'll note that that is the same as 7 pi over 3. So we can reduce that. But 7 pi over 3 is the same as pi over 3, right? We've got coterminal angles. So the key idea here and with these other points is that they are not unique, right? Every point can be represented in an infinite number of ways just by over-rotating coterminally as many times as we want. So it's a little bit different than in rectangular coordinates, where if I say 3, 4, that's the only way you can represent that coordinate is as 3, 4. So just keep that in mind. We don't have that uniqueness, so measuring angles in a particular way is going to be a skill that we kind of develop. So this is the same as 3 pi over 3. So we'll just note these are all the same coordinate. So 3 pi over 3 is going to be here. Okay. So we've got some additional points to graph here, which I'll let you graph on your own. Again, polar coordinates are not uniquely determined, so they can be represented in multiple ways. What we can kind of mention is a couple of things, though. So we've got polar axis, we've got the pole, oh, not the pole. Theta equals pi over 2. And then we do have the pole as the origin. We can have all of these symmetries as well. So it may be worth it to think about what each symmetry might look like. So note, if we have r theta is this point here, it can be symmetric about the polar axis. It could be symmetric about the line theta equals pi over 2, and I think I measured that out, not quite right. Or it could be symmetric about the origin or the pole. Oops. There we go. And so for each one of those points, we can represent those in different ways as well. So we'll just note this would be r negative theta. This coordinate could be r theta plus pi. So just adding pi to rotate 180 degrees. And this coordinate could be r comma pi minus theta. So we just subtract from 180 to get that point. But we could also use negative r. So we'll just note or. So in other words, we could measure in reverse to get the same location. And this is going to matter in terms of symmetries because, sorry, not the original coordinate. Although I guess we could do the original coordinate, but don't need to do that since we're finding symmetry about other locations. So we'll have negative r for each of these. So you might think about if you measured in reverse to get to that point, you would have negative r negative theta for symmetry about theta equals pi over 2. So you'd measure to the left r units and then rotate backwards. So you need to use negative theta. For symmetry about the origin, it's going to be negative r comma theta. And then for symmetry about the polar axis, if we did negative r, it's going to be pi minus theta. So those symmetry kind of calculations may matter, especially when we're thinking about graphs and behaviors of graphs. All right. So we're going to convert from Cartesian to polar and vice versa. So we'll note these are x, y, and we want them to look like r theta. So we're going to need to find r and theta, obviously. So r is going to equal the square root of the sum of the squares of x and y, and theta is going to be arctan of y over x, which is just going to give us negative 1 over 1, which is negative 1. And then for b, we're going to have r is equal to the square root of 36 plus 27, so we get rad 63, so almost 8. And theta is going to be arctan of 3 rad 3 over negative 6, which is going to be arctan of radical 3 over 2, negative radical 3 over 2. So we'll note we've got radical 2 for our r there, and then arctan of negative 1. Now the other thing that we have to recognize is where those coordinates are located. So we'll note that this coordinate is in quadrant 4, so we're going to need an angle measure that would be at that location. So we have two choices here. It could be negative pi over 4 or 7 pi over 4. And so you can choose which one you want it to be. So radical 2, I'll use the positive angle measure, 7 pi over 4 would be our coordinate. Similarly, if we graph -6, 3, rad 3, that's going to be in the second quadrant. So we need an angle measure that will land us in the second quadrant. So then for arctangent, we're going to get, it's going to be a 60-degree reference angle. So it's going to be 2 pi over 3. And I guess you could do a negative angle measure, but I think we'll stick with the positive angle measure. So radical 63, comma 2 pi over 3. And then for switching polar to Cartesian, of course, we'll do the reverse. So we'll use our definition for x and y and just substitute directly. So if we have 2 pi over 6, that's going to be 2 cosine pi over 6 and 2 sine pi over 6. So that is going to give us, so pi over 6 is rad 3 over 2. Sine pi over 6 is going to be 1/2. So our x coordinate is going to be radical 3, and our y coordinate is going to be 1. And then for b, we'll have -3 cosine 7 pi over 3. And y is going to be r sine theta, so that's going to be -3 sine of 7 pi over 3. So now we're going to get -3. 7 pi over 3 is the same as pi over 3. So we're just in the first quadrant. So that's going to give us positive 1/2. And then sine of 7 pi over 3 is also in the first quadrant. So that'll just give us rad 3 over 2. So we're going to end up with, it looks like, -3 over 2 and -3 rad 3 over 2. So our coordinate is in the third quadrant, even though the angle measure by itself would give us pi over 3. But we're measuring in reverse because we have a negative r value. All right, so that's kind of the overview of looking at polar graphs. Graphing polar equations is going to be something that you'll want to review as well. So there's quite a few different kinds of graphs that we can end up with. So I've noted horizontal lines, vertical lines, lines with zero slope, or just theta equals, and then kind of a nice graphic of the graphs that we've looked at. So circles, cardioids, and limaçons, which fall into the family of just limaçon. But cardioid is the famous heart-shaped graph where A is equal to B. Rose curves, so rose curves with all sorts of different symmetries, and then lemniscates. So in most cases, the emphasis on graphing is going to be not super intense where you have to like memorize what the graphs look like. You can graph these by plotting on theta tables, but knowing the basic graphs is useful for certain examples. So the next part we're going to get into is derivatives and defining a curve C by using parameters that are polar instead of rectangular. So I'll stop the video here. We'll come back for the second part where we look at defining a parametric equation for a curve using polar coordinates. So if you have any questions, shoot me an email. Otherwise, come by the office hours. And until I see you next time,